this, in fact, most of it has to do with reactions. So while you should look at those study guides, the key to learning the material and doing well on the test is the reactions. And I've taken the reactions out that you're responsible for in a continuous list, not, they're grouped by chapter, but not labeled that way. But everything involves alcohols, ethers, and alkenes. So those three classes of compounds. This is your first look at alcohols, your first look at ethers, and your first look at alkenes. What we had covered before dealt with alkanes and cycloalkanes, and then with alkyl halides. Now, you know that all of this about chemistry has to do with physical properties and chemical properties of molecules, and the relationship between the structure of a molecule and those physical and chemical properties. We spend a lot more time talking about chemical properties, and those are clearly the most difficult thing for students. Reactions, in particular, are very detailed and usually the largest problem for students learning organic chemistry. Reactions are hard. And it's not a case of just memorizing reactions, but individual reactions often represent whole classes of reactions that are tied together by what's called a mechanism, like an SN1 or an SN2 or an E1 or an E2 mechanism that doesn't only apply to alkyl halides. There are only a few mechanisms by which all organic reactions proceed. There are lots of different types of reactions with different labels, but only a handful of common pathways for reactions. So the trick to managing this jungle of reactions is to tie everything to these mechanisms. In terms of the properties, remember the physical properties, the biggest deal in physical properties is polarity. The polarity of a molecule, how polar it is, has the most to do with its physical properties. Molecules that are very, very polar tend to have high boiling points, water solubility, everything associated with strong attractive forces between molecules, sometimes hydrogen bonding, etc. The nonpolar molecules tend to have lower boiling points, less attractive forces, and everything that goes with that. Now, polarity is a very complicated thing. There actually is no one accepted definition for the polarity of an organic molecule. And it's actually very hard to measure in a way that puts a number on it. But the least you should do is have a general feeling for it. And what most organic chemists anyway do is put it into this large, medium, and small format. So you have your polar molecules, your nonpolar molecules, and then your moderately polar molecules in between. So the nonpolar molecules that you've seen so far would be alkanes and cycloalkanes and alkyl halides. That's the bottom of polarity. You've seen the top also now in the alcohols. The alcohols are the most polar class of organic compounds. But there's a lot in between that we call moderately polar. For instance, the ethers. That's really the first class of moderately polar compounds that we're looking at. But there are lots of others that fall into that gray area. So very polar, typically you need to have an OH in the molecule. Non-polar, just carbon-carbon, carbon-hydrogen, and maybe carbon-halogen bonds. Even though those bonds, carbon-halogen, are polarized, the molecules still behave as if they're relatively non-polar. So the alkyl halides are in the non-polar category, but a little more polar than the alkanes. It's all real, just common sense. Polar bonds lead to polar molecules. Now, in terms of the reactions, that boils down to specific reactions. You've seen reactions only in the chapter on alkyl halides. Remember, alkyl halides have this polarized carbon-halogen bond. That's, if you will, a chemical hotspot in this molecule. The carbon-halogen hydrogen bond is relatively stable, but the carbon-halogen bond is considerably weaker than any other bond in the molecule. And this is where you ran into really the most important type of reaction, this nucleophilic substitution. But you also ran into
broken, I guess.
competing reactions called elimination reactions. There was an SN1 mechanism and an SN2 mechanism, and also an E1 and an E2. They go together because if it takes something like the hydroxide ion, that's what we call a good nucleophile because it's electron rich, and nucleophile behavior is when the nucleophile attacks a carbon and attempts to form a bond to it. And this is typically an electron deficient carbon. But you know that the hydroxide ion is also a base. Base behavior is not the hydroxide ion attacking an electron deficient carbon, but pulling a proton off, and not from the carbon where the halogen's attached, which would seem to make sense, but actually it turns out that there's an easy path for elimination if the base pulls a proton off a carbon next to the halogen carbon. So it's what we call a 1,2 or a beta elimination. Now for the nucleophile behavior, it's SN2 if the halogen, which we call the leaving group, is still attached and the nucleophile helps to push it off. That's a one-step with bimolecular kinetics, second order. The SN1 is a difference in timing where because of a collision, the leaving group has left and produced the carbocation, and then, later, sort of as an afterthought, the nucleophile bonds to the carbocation. That's the two-step SN1. Difference between the SN2 and the SN1 is in the timing of the leaving group departure. And otherwise, there's no real difference unless this carbon is asymmetric, and then you know that a carbocation destroys that asymmetry and leads to a racemic mixture. Only the nucleophilic substitution, that's the SN2, preserves the optical purity, although it inverts the configuration because we find experimentally it's a backside attack. The elimination, which can be going on at the same time with other molecules, would be a different kind of collision where what would have been a nucleophile now behaves like a base and collides with one of these beta hydrogens, and that leads to either a single one-step elimination of HX. So as the base pulls on that proton, the carbon-hydrogen bond warps into a pi bond, and the leaving group leaves. So it's like a set of dominoes. It's all in one operation. Everything falls. That would be the E2 mechanism, one step. The E1, like the SN1, is a difference in timing where the leaving group has already left. You have a carbocation, and the base then pulls off the proton, and the pi bond forms and cleans everything up. So both the substitution and the elimination pattern one another in terms of the timing of the leaving group. E1, E2, SN1, SN2. And all that you need for this type of situation to occur is a carbon with a good leaving group. That would be an electronegative group, so the bonds polarize, but also as the leaving group departs, it needs to be relatively stable, or as stable as possible as the leaving group. If it's not very stable, then the equilibrium is going to push it back, and you're not going to have a very successful reaction. So, when you get into alcohols, all of this comes back. Because while the OH group is not a viable leaving group as the hydroxide ion, if you put an alcohol in acid, which would produce at least some protonated alcohol, that OH, this is very, very important to the chemistry of alcohols in acid, that OH gets protonated and becomes an excellent leaving group, better than a chlorine or a bromine. So this whole business of nucleophilic substitution and basic elimination comes up again, but not with alkyl halides, where the halogen is the leaving group, but with alcohols in acid, where the protonated OH is an excellent leaving group. So a nucleophile can displace water as the leaving group, or a base can pull off a proton and create the carbon-carbon double bond. So nucleophilic substitution and elimination comes up all over again in the chemistry of alcohols. The substitution ultimately replaces the OH with another group. Just to give you an example, if you react ethyl alcohol with the strong acid HBr, remember the acid HBr is quite capable of protonating the OH group, and it only has to do it even to a minor extent because it is in equilibrium, and more of the protonated OH can be created if that protonated OH reacts. So in HBr, you now have a bromide ion and a protonated alcohol. And so even someone who had never seen this reaction before, the reaction of ethanol with HBr, if they knew about nucleophilic substitution and knew that you could protonate an OH, this reaction would be kind of a no-brainer conclusion. It's exactly the same thing. It's nucleophilic substitution. And you get ethyl bromide plus water. And it's very important that you see this as just a nucleophilic substitution reaction, because that means you've seen it before with nucleophilic substitution of an alkyl halide. It's just a different leaving group. So, if you look at some of these reactions, this will come into play. Now, having said that, let me just add one more thing. This business of oxygen in the presence of an acid You can protonate the oxygen anytime you want if you have an acid present, because the oxygen is a Lewis base. But there's another advantage. Because it's a weak Lewis base, you can unprotonate it anytime you want. So the nice thing about reactions of oxygen in organic compounds with acids is if you want the proton to be there, feel free to do it. If you don't want it to be there, feel free just to erase it. Now, it's not disappearing, it's moving to another oxygen in the system, but there are usually plenty around. So that's one of the tricks that you can use to figure these reactions out. Don't let a protonated oxygen confuse you with its strange appearance. Just take the proton off. Okay, so having said that, going back to this list of reactions. Now, the first one actually converts an alcohol into its conjugate base, the so-called alkoxide ion. Because in addition to being basic on the oxygen, the OH is somewhat acidic, more acidic than any CH. So with a strong base like sodium hydride, you can make the so-called alkoxide ion, like Neth oxide or F oxide. That makes for a very good nucleophile and a strong base. So for instance,
Restart it. Oh, thanks.
the reaction of ethanol with sodium hydride would produce sodium ethoxide and hydrogen. Now, the ethoxide ion, CH3, CH2O minus, right here, is a very good nucleophile base species. It can act as a nucleophile and it can act as a base, just like the hydroxide ion. RO minus parallels HO minus. So if I were to make the ethoxide ion, and then ask you to react that with, say, benzyl chloride, you should know that this could involve either a nucleophilic substitution or an elimination. Because you have a nucleophile base species with that dual personality and an alkyl halide with a good leaving group. Now, elimination cannot occur from benzyl chloride because there are no hydrogens on the beta carbon, beta to the CCl. So elimination is really not an issue here. It can only be substitution, and the expectation would be that having taken organic chemistry, you could look at this and say, well, this would be a nucleophilic substitution. The ethoxide ion oxygen is a powerful nucleophile, and it's going to displace the chloride ion leaving group. And that would make this ether. That's a good way of making ethers by using the sodium salt or potassium salt. The metal doesn't really matter. You can make these salts with any metal, calcium, potassium, etc. But sodium is the most common, and an alkyl halide. In fact, that's this reaction right here. RO minus plus R prime And the R prime means that this R and this R don't have to be the same. You can see here, they're not. One alkyl group is an ethyl group, and the other is a benzyl group. So it makes benzyl ethyl ether, which is actually a fairly common industrial compound called phenol. It's used in perfumes. Smells like roses. This ether synthesis is called the Williamson ether synthesis. And generically, it's RO minus plus R prime X gives RO R prime. Now, the R prime X has to be primary only. And that's because if R prime is secondary or tertiary, you get a lot of elimination. Let me give you an example of that. If you take the potassium salt, put this potassium ion here, potassium salt of T-butyl alcohol, which is called potassium T-butoxide, you can buy it, and react that with methyl chloride, you get nucleophilic substitution. In addition to potassium chloride, you get T-butyl methyl ether, or methyl T-butyl ether. And in fact, this is also a well-known industrial compound called MTBE. You may have seen it if you have a sharp eye. It used to be on the gas pumps when oxygenated fuel was sold during a particular portion of the year. Yes?
That's KT, next to the oxygen in the first.
That's what?
Is that KT?
That's a potassium ion. That's potassium salt of T-butyl alcohol. Could have been the sodium salt. Methyl T-butyl ether was added to gasoline for many years to get around the air pollution restrictions from the federal government. If a state, and New Jersey is a prime air pollution state, exceeds certain levels of pollutants in the air, then there's a heavy fine that the state has to pay. To get rid of that fine, at one point a deal was struck where this methyl T-butyl ether was added to the gasoline, particularly during the winter and the following spring, and that was supposed to reduce emissions and let us off the hook in terms of the EPA imposed fine. Well, it did no such thing. It actually has no effect at all on air pollution. It took about 5 years for people to say, okay, enough is enough, get it out of the gasoline, and there's now another additive that's being put in the gasoline to reduce the emissions. And unfortunately, methyl T-butyl ether has gotten into the ground through leaking gas tanks, and unlike gasoline, which dissipates because it's a non-polar hydrocarbon, this ether is polar enough to adhere to particles in water, and so there's virtually no groundwater in New Jersey that isn't contaminated with methyl T-butyl ether. If you're drinking water from any groundwater source in New Jersey, you're drinking some methyl T-butyl ether. It's not a natural product. It's just one of those political things that got out of control. Anyway, it's still used a lot for other things. But that's the Williamson ether synthesis. Now let me reverse the roles here. Now this is the nucleophile, and this is the compound with a good leaving group. And of course this reaction is just nucleophilic substitution. And since it's not a secondary or tertiary alkyl halide, it's probably SN2, which is the best kind. Now, if you reverse these roles, so that I'm using sodium methoxide, so the OCH3 part is now the nucleophile, and I'm using T-butyl chloride as the alkyl halide. This leads completely to elimination. Because tertiary halides, as you know, have too much steric hindrance to substitute. And so the methoxide ion just starts taking over as a base, because it can't perform as a nucleophile, and you've got 9 beta hydrogens there for it to feed on, and so it simply removes HCl from 2 adjacent carbons and produces that alkene, which is called isobutylene. So depending upon the 2 roles, you get 2 totally different products. The top one is substitution, because I'm using better than a primary, I'm using methyl chloride. Any primary halide substitutes equally well, but not a secondary or a tertiary. If you use a secondary or tertiary, you get elimination. So if you want the Williamson ether synthesis, your alkyl halide portion has to be primary, or you're going to get elimination. So that's why that's written in primary only. Otherwise, it's a very good nucleophilic substitution reaction. Now, you can also make the alkoxide ions with plain sodium metal, just the way you make sodium hydroxide by putting sodium metal into water. So that's just an alternative way of making RO minus. This reaction here, I just had up on the board, ROH plus HX goes to RX. The key to that is to see the HX protonating the OH, and then the X minus substituting for the water. If you're not paying attention, and you're not going to study this, you're going to get this wrong. You cannot survive this test coming up by memorizing these reactions. You must animate them as processes. And been doing this for a long time. Nobody gets away with memorizing a list of reactions this long. Nobody. I don't care if you're Rain Man, you're not going to get this done. So don't even try. Put the time in, work at it. The way it will pay off is that regardless of whether you're a biology major, a biochemistry major, a pre-med or whatever, you're going to understand these reactions and not forget them. You can resurrect them. A year from now, 2 years from now, if you're sitting taking an MCAT test or a DAT or whatever, you're going to remember this and figure it out when you see it. If you try to memorize these reactions, you're going to have a complete mind wipe 2 weeks after the test, and you're not going to do well on the test. And I'm not trying to scare you, I'm just trying to help you. You have to dig into